Last time we talked about science being a lot more than just a technological driver, being much more than just a sort of utilitarian thing that gives us widgets and devices. It does give us that, but it gives us much, much more. It gives us an understanding of the universe. Moreover, it gives us a way of thinking about things. But we need to be careful and not get too evangelical about it, because although we'd like to think everything is nicely objective, and we do our best to make things objective, there are always issues in terms of objectivity and bias. And moreover, we need to be careful to realise this. We need to adjust our beliefs in the light of new information. And sometimes that's very difficult. The type of research I do, what we do in the nanoscience group, where we're looking at single atoms, single molecules, moving those around, making measurements of those, ideological bias really isn't an issue. If you're in political science, whatever you think of political science one way or the other, but if you're in that type of research area, your own personal ideology and your own personal, are you left-leaning, are you right-leaning, are you sit down the centre, are you communist, are you full-blown capitalist, all those type of things are brought to bear in how you make sense of data. And sometimes it's very difficult to let go of those biases, or in the light of new information, particularly when it counters your own ideology, runs counter to your own ideology. So today we're going to look at inductive versus deductive reasoning. This separation between inductive and deductive reasoning, which I'll explain, is why I titled last week's session Science Proves Nothing. And I'll spend a little bit more time on, a lot more time on that. Starting off with Francis Bacon and the whole idea of inductivism. Is science really organised skepticism, as it should be? The scientific method, however we might define that, and is there an archetypal scientific method? And like last week, we mightn't quite get onto proper and falsification, but we will get much of the way there. So just to remind you, in terms of the assessment, 2 pieces of assessment, one due in November the 15th, the other due in December the 20th. And I will stress again that the purpose of this module is very different from other modules in that it's not about me giving you out material, and then you take that material in and you write an essay in terms of regurgitation, or at least a sort of paraphrasing of that. It's about you trying to take the context and trying to take the arguments within this module and agree or disagree, fall somewhere down the middle, or strongly oppose. But it's more the ethos of the module rather than here is the information for you to make sense of. And you might, the feedback on the module year in, year out is pretty good, and there are some nice comments, but one thing I fail on is structure. You say that this module isn't particularly well structured. That's entirely deliberate. It's not about here's point 1, subsection 1b, 2.72a, whatever. It's not like that. It's a lot more free-flowing and a lot more loose than that. But that's your coursework. And if you've got ideas already about something you'd like to write about, for example, one thing that's coming up this week is Nobel Prizes. Are the Nobel Prizes a good idea? Are they fully representative of science and physics? Is that how we really do physics? Or do you think it's good to have sort of the equivalent of the Oscars in science? Recapping again from last week, we talked about Bayes. We'll be coming back to this a lot in future sessions. But that's the key point. Your brain is always making use of prior information to make sense of new information coming in. You're continually adapting your belief in the evidence. I talked about 2 key aspects of where you can give exactly the same information to 2 scientists with the same background and largely the same degree of expertise, and they reach dramatically different conclusions. Obviously taken from my own particular research area, I mentioned these stripy nanoparticle things, where one group, or a number of groups indeed, believe that what they're seeing here are real features. We believe otherwise. And then the question is, how do we decide? And if objective evidence and data analysis doesn't persuade the other side, what will? And they could make the same argument about us. So, was that. And then the other example, which is slightly less contentious but still also very interesting, are these intermolecular features, which a number of groups, an increasingly small number of groups now, but a number of groups hold to the idea that what they're seeing here are actually true intermolecular features, that they're seeing hydrogen bonds or some type of other intermolecular feature. And again, how do you decide? Both sets of papers are published in the peer review literature. So in one sense, they've passed the gold standard, the quality control for science. And is it just the weight of papers? 100 papers over here, disagree. Does that necessarily make these 100 papers right? Or, and increasingly this is how we are judged as scientists, if this group of papers has 10,000 citations and this countering group of papers only has 100 citations, does that mean that this side's definitively wrong? Is it really the weight of evidence? There are difficult questions. And this continues. This was 2017, but there are even more recent papers that have looked at these intermolecular features. Some people interpret them as effectively artifacts of the technique, of the scanning probe technique. Others see them as true bonds. So it's an ongoing controversy, it's an ongoing debate. Okay, a little bit about logic and reason, and a little bit about philosophy of science. This is only 10 credit module. We've only basically got 11 sessions. You could spend those entire 11 sessions not beginning to scratch the surface of the philosophy of science. So again, it's like I'm drip feeding you some of this stuff. Hopefully, what I'd like is that you go away, if you get interested in this stuff, go away and read up some of the references. In particular, Ladyman's book is a wonderful introduction. So, and from Ladyman, logic is the study of reasoning abstracted from what that reasoning is about. So, we have premises and we have conclusions, and the conclusion follows logically from the premises. So this is a good argument. All human beings are mortal. Socrates is a human being, therefore Socrates is mortal. Premise, conclusion. All Dachshunds are good physicists. Daisy is a Dachshund, therefore Daisy is a good physicist. Perfectly valid argument. Conclusion follows completely from the premises. Study of reason and abstracted from what that reasoning is about. That's absurd, of course. Well, I think it's absurd. You never know. But the important thing is that the argument works. It's an entirely valid argument. Here's not a particularly valid argument. All Dachshunds are good physicists. Edward is a good physicist. Therefore, Edward is a Dachshund. Or alternatively, all human beings are animals. Daisy is an animal, therefore Daisy is a human being. They're invalid arguments because the conclusion doesn't follow directly from the premises. Make sense? I think you all intuitively know this, but it's worth just putting these in place. This is another valid but bad argument. So it's valid in that if you take the premises as true, the conclusion follows. The Bible says that God exists. The Bible is the Word of God and therefore true, therefore God exists. Okay. I told you about my stance on religion last time. I'm not going to go any further than that, but it's worthwhile thinking about why that's a valid argument from one sense, but not a particularly good argument from another sense. So, and we're already, even with these few examples, we're already seeing that, it's not a simple black-white binary 1 or 0. Here's an invalid, but it's not necessarily a bad argument because it depends on the strength of the premises. I claim to be a physicist. Well, this Moriarty claims to be a physicist, except he claimed to be a mathematician. I have no reason to believe he is lying, therefore Moriarty is a physicist. So that's, it's an invalid argument because you don't know in terms of the premises. And moreover, as it says there, the conclusion could be false. But it's not necessarily an entirely bad argument depending on your belief, and that's what it boils down to, in the credibility of the premises. So, Bacon was really the first, or among the very first, to really think about measurement, empiricism. He's probably the first great empiricist, is probably the best way of putting it. In terms of, instead of doing what Aristotle and his colleagues did and think about, you know, everything is couched in sort of theory, we don't have to dirty ourselves, dirty our hands with measurements, just pure intellect can reach those conclusions, which is basically where the Greeks were. Bacon really tore that idea down. And he made the point that as well as having deductively, so arguments that are deductive, which means you've got that very straightforward, in some ways mathematical, you know, here are axioms, here is our conclusion. Or as we've seen, here are our premises, here is our conclusion. Science doesn't quite work like that, for reasons I will come to. And what we have is something which is a process of induction, whereby, let's say we have 50 gold samples, and we measure the electrical conductivity of 50 gold samples. We don't deductively know, as a matter of mathematical proof, that the 51st sample we measure is going to fall within the range of conductivities of those other samples. But what we do is we extrapolate and see if it works for n samples, or in parallel with what you've done in terms of mathematics by proof by induction. If it works for n samples, we see it's going to work for n plus 1 samples. But that's not a deductive proof. So, for this even to start to work, however, we need to have our observations and our measurements to be as free of bias or prejudice as much as possible, to make it a valid representation of the external world rather than representing our biases. And what Bacon argued is that instruments should eliminate the role of the unreliable senses. So it's instead of looking at things, use a microscope. But a microscope has a finite resolution. Even the best microscopes in the world have a finite resolution. Or a telescope has a finite resolution. Every instrument has some type of finite resolution. Moreover, at least at the moment, and artificial intelligence, as I mentioned last week, is an interesting contributor to this. At least at the moment, we analyse that data, and it's a human at the end who's analysing that data. And therefore, we bring to bear our interpretation of that data. Some people will see intermolecular bonds, other people will see an artifact. Indeed, depending how the artificial intelligence is trained, it will see intermolecular bonds or an artifact. Even if it's completely unsupervised and it's looking for patterns itself, without some direction, often it's going to get lost as well. Okay, so this is what I said. Induction, in the sense that Bacon used, and is pretty well the sense we use throughout, is the generalization from n cases to all cases. So let's think a little bit more about trying to remove those biases. And in terms of what Bacon said, trying to, let me bring up that point again. This, observation without bias or prejudice. Let's take something that isn't too contentious. This guy, some of you might recognize from a channel called Veritasium. Many of you are familiar with Veritasium? Quite a few, okay. So, this is a video from quite some time ago. It's a few years back. When he did, as you can see, 13 misconceptions about global warming. Global warming wasn't happening, so had to call it climate change, etc. Again, now, we have issues, as I said last week, in terms of the quality and the credibility of comments in any online forum. But in terms of the sociology and getting an insight into people's thinking, they're a good source of data, let's put it this way. So Viking here. This year was one of the coldest years in Michigan. Michigan, yeah, MI is Michigan, not Missouri. MO is Missouri. Michigan. Winter was longer, summer was cooler. With so much scientific data contradicting itself within the past 50 years, I find it hard to believe anything they say. Science is more faith-based than most people realise. And that gets our teeth on edge. We go, no, it's not faith-based, it's objective, and it's so much more than faith. It's completely polar opposite to religion or anything involving faith. Except, Okay, this is an interesting point before we get on to the main point. The data don't lie. I found this on a site which is really worth visiting called skepticalscience.com of just a couple of months ago. And you'll see these graphs where they take a very, very short time scale, and they even claim, as you saw there, that global temperatures are dropping over that point of view, over that time period. And this idea that the numbers never lie or the data don't lie, you probably know is not a particularly strong argument, but this brings it home really, really nicely. Okay, let me get on to the main point though. So this is from a survey. Which of the following statements about climate change do you agree with most? Climate change is happening and is mostly caused by humans. Show of hands. Climate change is happening and is mostly caused by natural processes. Show of hands. Climate change is not happening. Show of hands. Okay. So the vast majority are in here. The question is this. How do you know? Have you done the measurements? Have you run the simulations? Have you checked the simulations? Have you looked at the credibility of those measurements? Have you read the primary scientific literature inside and out and convinced yourself on the basis of each and every data point? Have you compared the theory yourself? Have you coded the simulations yourself? No, and neither have I. But I will stick my hand up for this particular category just as you stuck your hand up. Why? Because I trust the consensus. You trust the consensus. But, as our friend Viking says, let me get Viking back up. You believe what you and others presume to be professionals when they tell you something is fact, when they're able to write it down and provide evidence in whatever scenario. The thing is, you as an individual in most cases haven't done the research or have any of their facts in your own physical presence. Slightly convoluted wording, but you get what he means. So to believe professionals by word or written documentation is the very essence of faith. No need for name calling. You can guess why he's added that. And how quickly this descended into a massive flame war. But you get the point? I think you quite clearly argue that, well, actually, in principle, you can go back and in principle, you can look at that data. In principle, the data is all there. Sometimes that's true. Other times, for example, you might have heard of something called ClimateGate. Have you heard of something called ClimateGate, which was it's probably nearly a decade ago now, whereby University of East Anglia, who'd done a lot of climate change, research on climate change, had their entire emails hacked by climate deniers and released. And there were some statements in there that caused many of us, even those of us who aren't climate change scientists or climate scientists, to really wince, because they were saying, well, they'd use data protection to not release data. They'd use, publicly funded data. They said shouldn't be released out to the public. I personally think that's a mistake. There are arguments in the other direction, and you might hear about some of those arguments from Harry Collins when he's here for his invited seminar. But there is the issue here is that how do we counter that? How do we make a valid, strong counter-argument to what Viking is saying there? And that was a few years back, as I say, and this is really, Trump, Brexit, etc., this has really come to the fore. I mentioned this last week. It's a wonderful book. It's well worth getting. But that's where we are, where expertise is seen to be a disadvantage many times. That you seem to be part of the global elite or whatever. Okay, back to the comparing Aristotle versus Bacon, back to the inductive versus deductive thing, reason. Aristotle, first formal study of logic, and as I said, it entirely revolves around deductive reasoning, pure logic of the intellect. Very little to say on inductive reasoning, if anything, as it says, they're arguing from the particular to the universal. It works for n samples, it works for n plus 1 samples. Reasoning in which, and this is from Wikipedia has its moments, reasoning in which the premises seek to supply strong evidence for, and emphasis mine, not absolute proof of, because you can't have absolute proof of, the truth of the conclusion. No place for experimentation in Aristotle's logic. And you can make the argument, of course, with mathematics, mathematical framework, you can have deductive proofs where everything follows. But the interesting thing is that pretty well any mathematical framework has some axioms that are taken to be, in inverted commas, self-evident. So there is a stopping point in terms of where the logic ends and where you just have to say, I accept these things. We won't get into that, but it's an interesting, in terms of additional reading, it's worth taking a look at that. I can give you references if that's something you're interested in. In terms of Aristotle's logic, there's no place for experimentation. We just take these things as, from the intellect. We don't need to test them, etc. And that idea of sort of the beauty of the sort of intellectual world, or the beauty indeed of the mathematical world, this is a fantastic book. Sabine Hossenfelder. It's been pretty controversial, where she says that theoretical physics in particular, well, theoretical physics exclusively, and particular aspects of theoretical physics, including particle physics, are really losing their way because the focus is on the mathematical framework. The idea that really what we need to find, hence the title of the How Beauty Leads Physics Astray, is we need to find mathematical theorems, mathematical results that are appeal to our aesthetic sense, appeal to our sense of beauty, and somehow that's what's guiding us along the right path. But the science, nature might just be ugly. Granted, we've got good evidence. We drill into you time and time again the importance of symmetry, and symmetry is an exceptionally important guiding principle in physics. But again, we're sort of taking that. We've got good examples that it works in many cases, but can we extrapolate it to every single case? Is the idea of symmetry, or indeed supersymmetry, is that something that is necessarily there, or is it just wishful thinking on our behalf? And Sabine's book is really good at teasing out these arguments. Back to Bacon. Knowledge is power. And so, I'm not even going to bother trying to pronounce it because I'll just embarrass myself. But this was Francis Bacon's response, effectively, to Aristotle's organon, which was sort of organising principles in terms of the natural world. And novum for new, because it's distinct from what Aristotle said. All about organised skepticism. This is what Bacon said, almost in an echo or forerunner of what Sabine Hossenfelder writes in her book about using the mathematics to give you an anticipation of nature. And yes, that works sometimes. Antimatter is a wonderful example, where positron was predicted from purely the mathematical framework. But of course we then went and verified the existence of the positron. What really worries me, and I'm a dyed-in-the-wool experimentalist, and I'll bring that up again, Hossenfelder really goes into this in her book, is that there have been claims or arguments that we should move towards what's called post-empirical science, where because we can no longer go on building ever more energetic particle accelerators, that we're going to have to reach the point where we just can't probe matter on those energy scales or those length scales. And we're just going to have to allow the mathematics to guide us. And the mathematics in isolation, hence post-empirical science. To me, that's faith. That's religion and faith without connection to real empirical measurement, however that might be defined, but without that empirical test, experimental test, we're not doing science. Very happy to argue that point. And if that's something you'd like to think about writing about, that would be great. So, some great Colton Bacon. The human understanding is of its own nature prone to suppose the existence of more order and regularity in the world than it finds. As I said last week, we are great at looking for and finding patterns, whether they're there or not. This is available online. It's from over 10 years ago. Patternicity, finding meaningful patterns in meaningless noise. We're very good at doing that. It's even got a term, apophenia. As you can see, experience of seeing patterns or connections in random or meaningless data. This is from Alan Musgrave's book. The human understanding, when it has once adopted an opinion, either as being the received opinion or as being agreeable to itself, draws all things else to support and agree with it. Sorry, this is Musgrave quoting Bacon. And though there be a greater number and weight of instances to be found on the other side, yet these it either neglects and despises, or else by some distinction sets aside and rejects, in order that, oh, isn't that wording wonderful though, in order that by this great and pernicious predetermination the authority of its former conclusions may remain inviolate. Just as a piece of writing alone, that's wonderful. Such is the way of all superstition, whether in astrology, dreams, omens, divine judgments, or the like, wherein men, or women, having a delight in such vanities, mark the events where they are fulfilled, but where they fail, others happen much oftener, neglect and pass them by. If this agrees with our theory, wonderful, we get very, very excited. If this doesn't agree with our particular pet theory, we must have done the experiment wrong. Error bars are probably much bigger than we thought they were. Let's go and really hunt down and see if there's a systematic source of error that will push this in line with our theory. So we try to be objective, but there's objective and then there's objective. But with far more subtlety does this mischief insinuate itself into philosophy and the sciences, in which the first conclusion colours and brings into conformity with itself all that come after. It's very difficult to change our minds. If we get set on a particular idea, and particularly we've had a number of results that seem to agree with our particular theory, we will fight for that theory. And we'll say, well, no, it explains this, this, and this. And this idea, as we'll come to, the idea of Karl Popper was that what you want to do is falsify. Look for the evidence that falsifies your theory. That's in principle a good idea. In practice, it doesn't happen. Certainly not in physics. Okay, Milliken. So in terms of a good example, an experiment you're pretty familiar with, you'll remember the Milliken oil drop experiment. You're trying to determine the charge in the electron by having oil drops which get charged, and you're trying to balance gravitational force against the electrostatic force in the electric field. You remember this? I think even all the way back in first year you do a tutorial question. And Alex will have seen this before because I dug this out in a tutorial some time ago. But it's really quite interesting. This is Milliken in terms of what he wrote in his paper on the elementary electrical charge and the Avogadro constant. This is from the in that paper. It will be seen from figs 2 and 3 that there is but one drop in the 58, highlighted, whose departure from the line amounts to as much as 0.5%. It is to be remarked too that this is, that this is not a selected group of drops. This is not a selected group of drops. We're going to see that that was a lie. But represents all of the drops experimented upon during 60 consecutive days. Long after this was published, decades after this was published, they found Milliken's notebooks. And I think there's something missing from the top, is there? 170 drops, not 60, were actually measured. And those that didn't meet expectations were rejected. Beauty, publish. And then if you work down through the list, this is almost exactly right. How does he know? Because he's got a very set idea in his head of what the value should be. And the best one I ever had, 3 exclamation marks. Exactly right. Publish this beautiful one. Publish this surely beautiful. Error high will not use. Perfect, publish, won't work. Too high by 1.5%. 1% low. Too high E by 1.25%. Cherry pick, cherry pick, cherry pick, cherry pick. This is the reference is available there. It's a really good read. Flirting with Fraud, Milliken, Mendel, and the Fringes of Integrity. And then Omar, who unfortunately can't be with us today, but a couple of years back, informed me about this. This is the Hubble constant. And and the variation in the Hubble constant over a number of decades until we've converged here, but notice it's dropping off. Moreover, notice the error bars. This one's sort of getting close to the line, but these are pretty confident measurements that are entirely out of kilter with the modern value of the Hubble constant. Why is that? Well, Feynman, as ever, has got something to say on that. Not that particular result, but the Milliken result, and it also holds for the Hubble result. It's interesting to look at the history of measurements of the charge of an electron after Milliken. If you plot them as a function of time, you find that one is a little bit bigger than Milliken's, and the next one's a little bit bigger than that, and the next one's a little bit bigger than that, until finally they settle down to a number which is higher. Well, Smith et al. Got a number that wasn't like ours. We need to make sure that it's just within the error bar of what they got. We're not quite where they were, but what's the closest value we can say that will put us in the same ballpark as they were? In one sense, this is almost, I wouldn't quite say laudable, it's not laudable, but it's that they are, no, it's definitely not laudable. What I was about to say is that there is, they are assuming that somehow they've got the experiment wrong, which is always a good thing to do. That should always be your first part. But then what they're doing is they're very subtly changing their error bars or changing their final value so that they ensure that they're not too far out of agreement with previous results. Let's hear Feynman say that a lot more eloquently than that. Why didn't they discover the new number was higher right away? It's a thing that scientists are ashamed of, this history, because it's apparent that people did things like this. When they got a number that was too high above Milliken's, they thought something must be wrong, and they would look for and find a reason why something might be wrong. When they got a number close to Milliken's value, they didn't look so hard. And so they eliminated the numbers that were too far off and did other things like that. We've learned those tricks nowadays, and now we don't have that kind of a disease. Sorry, it's really uncomfortable to disagree with Richard bloody Feynman, but he's wrong. He's really badly wrong on that. Just let me skip over that for a second. I'll come back to that. The thing is, I would say we're even worse at that now, because there are many more papers published, many more scientists. Therefore, the pressure on getting really high-profile, hard-hitting results with a really strong narrative is very, very strong. As I said last time, in terms of a career in science or an academic career, you've got to publish in those Nature, Science, Physical Review letters, those high-profile journals. And if it gets on the front cover of The Guardian or The Telegraph or The Times or Scientific American or whatever, all the better. But what is really driving the science is this is new, this is new, this is new. Isn't this amazing? We're all guilty of it to some extent, particularly those of us involved in 60 symbols. Isn't this amazing? Isn't this amazing? Isn't this amazing? New, new, new. Instead of what should be happening in science is a lot of checking of what's come before. Except that doesn't happen. So there are many examples. These were two very high-profile stem cell papers, just to show you that I'm not going to focus entirely on physics. But these were attracted, and unfortunately, one of the people involved with these, where the data was most definitely fraudulent, ended up committing suicide. That's how high the stakes are. Because they not only took down their own work, they took down the work of the collaborators, and they cast a massive shadow, to put it mildly, or indeed, many of the researchers involved in that work are going to find it very difficult to move on to different careers, or move on in science, pursue their career, pursue their dream, pursue what they wanted to do. So there's a massive focus over the last number of years. It says data processing and ethics in science. And there's data processing in terms of if you've got an image, where is the line in terms of processing that image? Is contrast enhancement okay? Is looking around with the RGB values okay? Cutting and pasting okay? Where do you draw the line? Or do you just, I think many of us in physics would be of this opinion. You just have the raw data as it came off the machine, the instrument. You give as much information about that raw data as possible. Something called retraction works now, which actually looks at those papers that have been retracted. There's also something, and we'll come back to this a few weeks' time, something called Popaia, which is what's called a post-publication peer review, hence Popaia site, whereby papers that are in the literature or anything which has a digital object identifier can be uploaded to Popaia and a discussion can be started on it. The problem is, for decades, we've had the idea that the way science works is you write your paper, you send it off to the journal. First of all, you have to get past the editors of the journal, and they are looking for something newsworthy. And then you have to get past the referees. 2, 3 referees. And if you get past those referees, then the paper's submitted, and almost that's where the science ends. When in fact that's where the science should begin in terms of that paper being submitted and published. And the thing with Popaia is it takes those published papers and opens up a discussion on those published papers. And it's been a long time coming, but it's a key, I think it's a really good development. There are issues with it, particularly with regard to the role of anonymity in reviewing those papers, but we'll come back to that. As I said at the start, if you've got thinking of topics to write about, if any of you are interested in this, I'd love to read what you have to say, given that it's tomorrow, I believe, the Nobel Prize will be awarded. The question is that really how science is done? You know, when it came to the gravitational wave Nobel Prize, 3 people got it? Hundreds, thousands involved in that activity. So it's got its pros and cons. It's great because it brings science into the limelight. It's got its cons, though, in terms of it gives a rather skewed and distorted picture of how science actually works. Okay, back to Bacon. This is a fantastic quote. The understanding must not be allowed to jump and fly from particulars to general conclusions. The understanding must not therefore be supplied with wings, but rather hung with weights. You want to be your own worst critic. Just think it's wrong. First, if you see an incredible result and you go, oh, this is incredible, I can't believe this has happened. Usually, when you say you can't believe it has happened, you're right in that first interpretation of the data. Now, this has never been done back in 1620. When it is done, we may entertain better hopes of the sciences. Sorry to keep referencing Feynman, but you know, a lot of this stuff he says very pithily. The first principle is that you must not fool yourself, and you are the easiest person to fool. Right. So Bacon came up with 4 idols, 4 things, biases really, that we need to guard against. So, idols of the mind. Idols of the tribe, which means effectively peer pressure. Seeing order patterns where there are none. Wishful thinking, jumping to conclusions. Idols of the cave, personal or ideological preferences. Idols of the marketplace. Right, so this is, don't get in terms of free market into your head. I actually misinterpreted this for a while. But when he says idols of the marketplace, he basically means, for example, we'll talk about a vector. Biologists will talk about a vector. What we understand by a vector is very different to what a biologist understands about a vector. Or we'll talk about work. Political scientists will talk about work. They do not mean the integral of the dot product of the force times the displacement vectors. Those are dramatic differences, but there are also subtle differences. We collaborate with computer scientists, for example, a lot, and have collaborated with chemists and biologists, and there are different working methods. And sometimes the thing that really holds you back is the jargon. Sorry. We're going to close in 5 minutes or so. And this idols of the theatre, being wedded to a particular philosophical framework. So different, what's best to describe these? Different types of prejudices, different types of ideologies, different types of ways of thinking, how they can make you much less objective than you'd like to be. People writing stuff down. Good. So Bacon's inductivism. Observation followed by induction, which is fairly clear. Observation must be based on methods which minimize the influence of those four idols we mentioned. Generate set of observations, and of course, even before we do that, the choice of the instrument you use to generate those sets of observations. So if I want to look at, I don't know, texture or topography in a polymer sample over a range of tens of microns, my technique of choice will always be scanning probe microscopy. Others might want to use optical microscopy, others might want to use some type of X-ray or neutron scattering. And depending on your technique of choice, although the sample's the same, the way you collect, generate, and interpret those observations can be very, very different. So even your selection of experimental technique, or indeed, do I use this photomultiplier or this photomultiplier, this preamp or that preamp, all of which mean that getting a completely objective set of observations is actually quite tricky. But we assume these are observations are as objective as they can be, and then we go further and we generalize. So that's where we get F is equal to GMM over R squared, PV is equal to nRT, Snell's law, whatever. Take your equation of choice. Okay, so that's what we had before. But there are issues with this. We don't do experiments. We don't set up and just start off doing an experiment complete, blanking off what has come before. We go and look at the literature. We read how others have done this experiment. We think about how might we improve on that. So we don't do experiments with no preconceived ideas. And we definitely do not disregard expertise. In fact, the whole peer review system, we read those papers and we know, well, this group's pretty good. They've got a good reputation, they've got a good profile. This group might be okay, but I've never really heard of them before. I've never seen them present at a conference. They seem to be quite new to this field. Now, this group could be much better than this much more well-established group. But still, your natural inclination, see this all the time in terms of how different research assessment exercises happen, where an awful lot is based on the number of citations to a paper. So how high profile that paper is, as distinct from its quality. Because just because a paper's got lots of citations doesn't necessarily mean that it's a high quality paper. Often it is, but sometimes it isn't. And to disagree with Feynman, it's not underpinned by a belief in the ignorance of experts. And does this actual inductivism actually work? XKCD again. You can read these at your leisure. We've got 2 minutes left. Okay. Actually, I think I'll leave it there. And because Hume's a good place to start for the next one. So as I say, I'll do a video thing on Hume, and then when we come back the week after next, not just Hume, many other aspects related to Hume. The week after next, I will have 20 minutes, and then it's over to you, and we'll see how that pans out. Okay, thank you very much for coming along. I will see you in 2 weeks' time.